Imagine you throw a ball, straight forward, and instead of flying in the direction you threw it, it drifts sideways. Not a lot, barely perceptibly, but measurably, consistently, in a direction that isn't quite where the throw should have sent it. You would want to know why. 3I/Atlas is being pushed sideways. Not dramatically, not enough to alter its path through the solar system in any meaningful way. The total offset after a month of sideways push is approximately half the radius of the Moon, negligible in cosmic terms. But the direction of that push is wrong. Or at least, it is not what the standard model of cometary outgassing predicts. And understanding why it is wrong requires understanding something fundamental about how force works in space, how scientists measure motion with extraordinary precision, and what the geometry of 3I/Atlas's jets tells us about the physics happening inside this object. Today we are going to build this from scratch. No shortcuts. We start with what non-gravitational acceleration is and why it exists. Then we look at what NASA's official model says. Then we look at what a new paper published March 3rd says instead. Then we look at what the jet geometry tells us. And we end with the honest answer to the question the title is asking. Is this sideways push natural? Or does it require a different explanation? I will not pretend the answer is simple. It is not. But by the end of this video, you will have the tools to evaluate it yourself. Let's start at the beginning. Gravity is not the only force in space. The first thing to understand is that objects moving through space are not subject only to gravity. Gravity dominates, but it is not alone. For a rock, a pure, inert, chemically dead rock, gravity is essentially the whole story. You measure the rock's position and velocity at one moment. You apply Newton's laws and Einstein's corrections, and you can predict where that rock will be at any future moment with extraordinary precision. The prediction matches observation to within the measurement errors. Gravity is sufficient. For a comet, the situation is different. Comets are not inert. They are active. As a comet approaches the sun, solar radiation heats its surface. Surface ice is sublimate. Gas escapes from the nucleus. And here is the key physical principle. When gas escapes in one direction, it pushes the nucleus in the opposite direction. Newton's third law, action and reaction. This push is called non-gravitational acceleration. It is real, measurable, and well understood in principle. Every active comet in our solar system experiences it. How is it measured? By comparing where an active comet actually is against where pure gravitational calculation says it should be. If the comet is consistently slightly ahead of, behind, or to the side of its purely gravitational position, something is pushing it. The pattern of those deviations, accumulated over months of careful astrometric observation, allows scientists to characterize the push. Its magnitude, its direction, how it changes with distance from the sun. The standard mathematical framework for characterizing this push was developed in 1973 by Brian Marsden, Zdenek Sekanina, and Donald Yeomans. They decomposed the non-gravitational acceleration into three components. A1, the radial component, pointing away from, or toward, the sun. A2, the transverse component, pointing along the direction of the object's orbital motion. A3, the normal component, pointing perpendicular to the orbital plane. These three numbers, A1, A2, A3, are what scientists are arguing about when they argue about 3I/Atlas's non-gravitational acceleration. Their magnitudes, their ratios to each other, what they imply about the physical process producing the push. What standard cometary outgassing predicts? Before we look at what 3I/Atlas actually shows, we need to establish what standard cometary physics predicts. What should A1, A2, and A3 look like for a normal active comet? The answer comes from understanding where outgassing happens on a comet nucleus. Solar heating is the driver. The sunward face of the nucleus receives the most radiation. It heats up most. Its ices sublimate most vigorously. Gas escapes preferentially from the sunward hemisphere. If you have a spherical nucleus, uniformly covered in ice, with no rotation, the gas escapes symmetrically from the entire sunward hemisphere. The net push, integrated over all that escaping gas, points directly away from the sun. The reaction force on the nucleus also points directly away from the sun. A1 dominates. A2 and A3 are small, or zero. Real comets are more complicated. They rotate. They have heterogeneous surfaces. Active regions, called source areas, exist where ice is exposed and sublimation is vigorous. Inactive regions, covered in refractory dust or depleted of volatiles, contribute little. The distribution of active regions on a rotating nucleus determines the net direction of the escaping gas, and therefore the net direction of the push on the nucleus. But even with these complications, the dominant push in a typical comet is still primarily radial, away from the sun, because solar heating is ultimately what drives the outgassing, and solar heating is strongest on the sunward side. The transverse component A2 exists, but is typically much smaller than A1. This is the prediction: A1 large, A2 small. The ratio A1 to A2 for a typical solar system comet is greater than 1, often significantly greater. What does NASA's official report say about 3I/Atlas? A1 is 5 times larger than A2, consistent with the standard picture: radially dominated push, away from the sun. A normal comet doing normal cometary things. The new paper by Spada, Kralikowska, and Dones says something different. The measurement problem, astrometry, and ITS challenges. Before we get to the disagreement between NASA and the new paper, I want to explain why measuring non-gravitational acceleration is difficult, because understanding the difficulty helps evaluate the disagreement honestly. Non-gravitational acceleration is measured by comparing observed positions against predicted gravitational positions. The positions come from astrometry, the precise measurement of an object's location on the sky, expressed as right ascension and declination. Modern astrometry is extraordinarily precise. Individual measurements can locate an object to fractions of an arcsecond, but the non-gravitational acceleration of 3I/Atlas is tiny. Loeb describes the total magnitude as approximately 1 micrometer per second squared at Earth's orbital distance. The spatial offset this produces over 1 month is half the radius of the Moon. Compared to the Earth-Sun separation, that offset is smaller by a factor of 200,000. Detecting this signal requires accumulating many measurements over many months. Each individual measurement has uncertainty, systematic errors, from atmospheric refraction, from telescope calibration, from the precise coordinates of reference stars, add up. The longer the observation arc, and the more measurements it contains, the better the constraint on the non-gravitational acceleration. But there is a complication specific to 3I/Atlas. In October 2025, the object passed behind the Sun from Earth's perspective. Solar conjunction. Ground-based telescopes could not observe it. This created a gap in the astrometric record at exactly the time 3I/Atlas was closest to the Sun, when its outgassing was most intense, and when its non-gravitational acceleration was largest and most rapidly changing. The pre-perihelion data and the post-perihelion data are therefore 2 separate observational arcs, joined by a gap we cannot directly observe. Fitting a smooth model of the non-gravitational acceleration across that gap requires assumptions about how the outgassing behaved during perihelion. Different assumptions produce different results for the fitted parameters, particularly for A2, the transverse component. This is why A2 is the most uncertain of the 3 components. A1 and A3 are constrained by the overall shape of the orbital deviation, which is robust to different modeling assumptions. A2 is more sensitive to how you handle the perihelion gap, how you weight different observations, and what functional form you assume for the radial dependence of the outgassing. Both NASA and the Spada paper are aware of these challenges. Their different results for A2 are a direct consequence of different choices in handling them. NASA's model, what Farnokia did and why. NASA's non-gravitational acceleration solution for 3I/Atlas was produced by Davide Farnokia, a navigation engineer at JPL with extensive experience in asteroid and comet orbit determination. This solution is what appears in the JPL Small Body Database, the authoritative catalog that the astronomical community uses for orbital planning. Farnokia's solution is based on 782 carefully vetted astrometric observations. That number is much smaller than the total number of submitted observations, which runs into the thousands. JPL applies rigorous quality filters. Observations that don't meet precision standards are excluded. The result is a smaller but, by JPL's criteria, cleaner dataset. The functional form Farnokia uses for the radial dependence of the outgassing has been updated over time. Initially, JPL used the standard Marsden water ice model, which assumes outgassing falls off steeply with distance from the Sun. Later, after the CO2-dominated nature of 3I/Atlas's coma became clear from Webb NIR spec data, the model was updated to a 1/ or superscript 2 dependence, appropriate for CO2 sublimation, which is less steeply distance-dependent than water ice. With this model and this dataset, Farnokia's solution gives A1 approximately 5 times larger than A2. The push is primarily radial, away from the Sun, consistent with the standard picture of solar-driven outgassing. There is an important historical footnote here. Avi Loeb noticed in late 2025 that the predicted closest approach distance of 3I/Atlas to Jupiter on March 16, 2026 was approximately equal to Jupiter's Hill radius, the distance at which Jupiter's gravity dominates over the Sun's. He sent an email to Farnokia pointing this out. He did not receive a response. But within days, NASA's JPL updated the A1 value, revising it downward by a factor of 6 and switching to the 1/ or superscript 2 CO2 model. The new prediction placed 3I/Atlas's closest approach slightly outside the Hill radius. Loeb noted this publicly. He did not accuse Farnokia of anything improper. He observed that changing the model changed the prediction, and that the new model's accuracy could not be confirmed because the perihelion passage, when most of the non-gravitational acceleration occurred, was hidden behind the Sun. That exchange matters for understanding the context of the Spada paper. The Spada paper, a different answer from more data. The paper by Federico Spada, Małgorzata Kralikowska, and Luke Dones was posted on AR14 on February 28, 2026. Its title is Precise and Technical, Systematic and Statistical Uncertainties in the Non-Gravitational Acceleration of 3I/Atlas. The authors are specialists. Kralikowska is one of the world's leading experts in cometary orbit determination, with decades of work on the orbital mechanics of long-period and interstellar comets. Spada and Dones bring complementary expertise in dynamical modeling and uncertainty quantification. Their dataset contains 7,788 reported astrometric epochs spanning May 8, 2025 to February 19, 2026. That is a factor of 10 more observations than JPL used. The larger dataset reflects a different methodological choice, using a broader set of observations with a carefully constructed error model, rather than a smaller set of individually vetted observations. The Spada team tested multiple functional forms for the outgassing radial dependence. Symmetric models, where outgassing falls off the same way before and after perihelion. Time offset models, where the peak outgassing lags behind the perihelion passage. Asymmetric models, where the pre-perihelion and post-perihelion falloffs are different. This last type is physically motivated by the observed behavior of 3I/Atlas, which faded faster after perihelion than it brightened before, evidence that its surface composition changed as perihelion depleted the near-surface CO2 reservoir. Across all these models, A1 and A3 are consistent. The radial and normal components are robust. They do not change much when you change the model or the data selection. A2 is different. For all of their comprehensive models, particularly the asymmetric ones that best fit the light curve behavior, A2 comes out comparable in magnitude to A1, not 5 times smaller, approximately equal. This is the finding that Loeb highlighted in his March 5 post. He summarized it precisely. The new paper suggests 3I/Atlas is pushed sideways and not simply away from the Sun. And then he added, yes, official statements from NASA can be wrong. Science is a learning experience. What a large transverse component means physically. Let me now explain carefully what a large A2, a transverse component comparable to the radial component, means in physical terms, because this is the heart of what makes the finding scientifically significant. Remember the geometry. A1 pushes the object away from or toward the Sun. A2 pushes the object along its direction of motion. A3 pushes it perpendicular to the orbital plane. If outgassing is driven primarily by solar heating of the sunward face, A1 dominates. The push is away from the sun. For A2 to be comparable to A1, the outgassing must have a substantial component directed along the orbital velocity, sideways relative to the sun-comet line. This requires gas to be escaping from a direction that is not primarily sunward-facing. How can this happen naturally? There are two mechanisms. The first involves spin axis orientation. A comet nucleus rotates. If the spin axis is tilted, the distribution of solar heating across the surface changes. Regions near the spin axis pole receive nearly constant illumination if the pole points toward the sun. Regions near the equator receive more variable illumination. If the spin axis is oriented nearly toward the sun, a near-sunward pole, the highest latitude regions receive the most persistent solar energy. Jets from high-latitude active areas emit gas primarily along the spin axis direction, which is nearly the sun-comet line. Their push is primarily radial. But if those high-latitude jets are slightly off-axis, if the spin axis is 20 degrees from the sunward direction rather than exactly on it, the gas escapes at an angle. The net push has a substantial transverse component. And if the nucleus wobbles, if the spin axis precesses or nods, the transverse component averages over a range of directions, potentially producing a systematic A2 of significant magnitude. The second mechanism involves localized, asymmetric active regions. If one side of the nucleus has more ice exposure than the other, perhaps because of cratering, fracturing, or erosion history, gas escapes preferentially from that side. Depending on the nucleus orientation and rotation, this asymmetry can produce a transverse push. This is related to what is called the thermal lag effect. Because the nucleus has thermal inertia, the maximum outgassing happens not at the subsolar point, but slightly past it, in the local afternoon. This is where the jets come in. The three jets at 120 degrees, what Hubble found. Avi Loeb and Tony Scarmato published two papers analyzing high-resolution Hubble Space Telescope images of 3I/Atlas. Their method, the Larsen-Cecchinina rotational gradient filter, removes the smooth, symmetric coma background by rotating the image and subtracting it from itself. What remains is the asymmetric structure, jets, streamers, surface features. Applied to the highest resolution post-perihelion Hubble images, this method revealed a specific and surprising morphology. Three mini-jets, symmetrically separated from each other by exactly 120 degrees, plus a fourth, more prominent jet pointing in the sunward direction, the anti-tail. The three mini-jets wobble. Their position angles oscillate with a period of approximately 7.1 hours, consistent with the nucleus rotation period derived from the light curve. The wobble is periodic and coherent. The jets are not random. They are tied to the rotation of the nucleus. From the geometry of the wobble, Loeb and Scarmato derived a spin axis orientation within 20 degrees of the sunward direction. The nucleus is spinning with its pole approximately pointed toward the sun. Now connect this to the non-gravitational acceleration. If the spin axis is nearly sunward, the three 120-degree mini-jets are at high latitudes on the nucleus, near the pole. Their outgassing directions are nearly along the spin axis, which is nearly the sun-comet line, but 20 degrees off. And three jets at 120-degree spacing around a pole that is 20 degrees from the sunward direction produces a net gas emission pattern that is not purely radial. Loeb's March 5th post makes this connection explicit. He writes that this configuration naturally favors strongly directional gas and dust emission, capable of generating a transverse acceleration component which is comparable in magnitude to the radial one. This is a specific, testable physical prediction. The jet geometry, as observed, is geometrically consistent with the A2 value found by the Spada paper. Two independent measurements, jet positions from imaging, orbital deviation from astrometry, pointing to the same physical picture. That is science working as it should, independent lines of evidence converging. The natural explanation and ITS limits. Let me now assemble the natural explanation for the sideways push, stated as clearly and charitably as possible, and then identify where it has limits. Natural explanation. 3I/Atlas has a nucleus with its spin axis oriented approximately 20 degrees from the sunward direction. 3 localized active regions, exposed ice sources, possibly related to the object's formation history or to impact cratering during 7 billion years of interstellar travel, are symmetrically spaced at 120-degree intervals around the nucleus. As the nucleus rotates with its pull nearly toward the sun, gas from these 3 high-latitude jets escapes along directions that are slightly off the sun-comet line. The aggregate push is both radially outward and transversely sideways, with comparable magnitudes because the geometry amplifies the transverse component. The spot of paper's large A2 is the orbital signature of this jet configuration. This explanation is physically coherent. Every element of it is individually plausible. Active regions on comet nuclei are observed. Spin axis orientations near the sunward direction are known in solar system comets. Localized jets producing non-radial acceleration are observed, but the natural explanation has 2 specific features that need examination. First, the 120-degree spacing. Natural active regions on comet nuclei do not spontaneously arrange themselves at equal 120-degree intervals. Active regions form where ice is exposed, at fractures, craters, scarps, or regions where erosion has removed the dust mantle. There is no physical mechanism that preferentially produces ice exposure at 3 equally spaced points on a nucleus. 120-degree spacing is a geometric regularity that natural processes do not obviously generate. Loeb acknowledges this directly. He calls the symmetric system of 3 mini-jets, separated equally by 120 degrees, enigmatic. Enigmatic is a precise word. It means, we observe it, we cannot easily explain it with standard physics, and we do not know what it means. Second, the combination of anomalies. A large transverse component might be explainable by the jet geometry. The jet geometry might be explainable by the spin axis orientation combined with active regions. But this comet also has CO2 to water ratios 4.5 sigma above the solar system trend. Methanol 4 times the solar system average. Post-perihelion eruptions from a deep interior. A Hill sphere coincidence with Jupiter of roughly 1 in 26,000 probability. Activity patterns inconsistent with standard thermal models. Each anomaly has a natural explanation. The question is whether their simultaneous occurrence in a single object is plausible. That question does not have a simple numerical answer. The question of propulsion, what it would require. I want to address the propulsion hypothesis directly, carefully, and without either dismissing it or overstating it. Loeb has raised the possibility, in multiple blog posts and in a paper co-authored with Hibbert and Crowell, that 3I/Atlas might be an artifact, a technological object, rather than a natural comet. He explicitly frames this as an open question, not a conclusion. He has been consistent about not claiming certainty. What would the propulsion hypothesis require to be true? It would require an object approximately 2.6 kilometers in diameter, traveling at 58 kilometers per second, that either is or contains an active propulsion system capable of producing a transverse acceleration comparable in magnitude to the natural cometary outgassing signal. The total non-gravitational acceleration is tiny, 1 micrometer per second squared. That is not a large force requirement, but it would need to be sustained over months with a specific directional signature. It would require that the 120-degree mini-jets are not random active regions, but directed nozzles or thrusters, spaced as they would be if designed for attitude control, which typically requires at minimum 3 non-coplanar force directions. It would require that the object's cometary behavior, its coma, its water outgassing, its dust tail, its molecular inventory, is either genuine cometary activity coincidentally covering an artificial object, or is itself generated as part of the propulsion or cloaking system. It would require explaining why SETI's Green Bank telescope observation on December 18, 2025, detected no technosignatures, no radio emissions above the detection threshold, no signals in the frequency ranges associated with technological transmitters. The absence of radio technosignatures does not rule out technology. A passive or non-transmitting object would not emit detectable radio signals. but it removes one obvious evidence type. The propulsion hypothesis requires a lot. The natural hypothesis also requires some unusual coincidences. Science does not yet have the data to definitively choose between them. What the Jupiter data will tell us. 10 days from now, March 16th, 2026, 3I/Atlas makes its closest approach to Jupiter. This event is not just scientifically interesting. It is a precision test of the orbital models that disagree with each other. Jupiter's gravitational deflection of 3I/Atlas during the flyby is calculable with high precision given the encounter geometry. What actually happens to 3I/Atlas's trajectory, how much it deflects, in what direction, will be measurable from astrometric observations during and after the encounter. If NASA's model is more accurate, the post-flyby trajectory will be consistent with its predictions. If the spotted paper's model is more accurate, there will be a measurable difference. The two models predict different pre-encounter positions for 3I/Atlas, which means they predict slightly different encounter geometries, which means they predict slightly different post-encounter trajectories. Within weeks of March 16th, the orbital models will be updated with the new data. The disagreement between NASA and the spotted paper will either narrow or deepen. The question of what is pushing 3I/Atlas sideways will become more constrained. Not resolved, more constrained. Let me summarize what we actually know, stated as precisely as possible. 3I/Atlas is subject to a non-gravitational acceleration. That is not in dispute. The object is not following a purely gravitational path. Something is pushing it. The total magnitude of that push is tiny, 1 micrometer per second squared, a monthly offset of half the moon's radius. Negligible for navigation, significant for physics. The direction of that push is in dispute. NASA's official model says it is primarily radial, away from the Sun, with the transverse component 5 times smaller. The spotted paper, using 10 times more observations and asymmetric outgassing models, finds the transverse and radial components approximately equal. 3I/Atlas is being pushed sideways as much as it is being pushed outward. Hubble images show 3 mini-jets at exactly 120-degree separations, wobbling with a 7.1-hour period consistent with a spin axis approximately 20 degrees from the sunward direction. This geometry is physically consistent with the large transverse acceleration the spotted paper finds. The natural explanation is coherent. The 120-degree spacing itself is enigmatic. Natural cometary physics does not obviously produce perfectly symmetric active regions. It is not impossible. We do not know how to assign it a probability. SETI detected no radio technosignatures. The molecular inventory is extraordinary but chemically natural. The non-gravitational acceleration magnitude is small. The honest answer to the question in the title, is this sideways push natural or propulsion, is, we do not know. The natural explanation is plausible. It has gaps. The propulsion hypothesis would explain the gaps. It requires extraordinary assumptions. The data are not yet sufficient to decide. What we can say is this. 3I/Atlas is the most chemically unusual, geometrically surprising, and dynamically complex object we have ever observed from outside our solar system. It is not behaving exactly like a solar system comet. It is not behaving in ways that are impossible for a natural object. And it is leaving our solar system in 9 days. The Jupiter flyby data will sharpen the picture. It will not close the question. That is exactly where honest science leaves it.